Here we have example 2 from Work and Energy Part 2. Our block is set into motion up the incline. For Part A, we want the change in the kinetic energy. That change will be negative because it's slowing down. So the change in kinetic energy is, as usual, final minus initial, which is 0 minus initial, so the change in kinetic energy is just the negative of what we started with. That's how much kinetic energy we lost. The change in potential of the block Earth system, well, for that we need how much the block has changed its height. So this change in height, h, is related by a similar triangle to this angle. So this height that we gain, you can get from trig, and so the gain in potential is the weight of the block multiplied by the height by which it increases. The friction force exerted by the block for part C. Remember, when we're on an incline, the normal force is not just equal to the weight. The weight vector points down, but we split this into components parallel and perpendicular. And in this case, our normal force is mg cosine theta. So our frictional force is the coefficient mu multiplied by mg cosine theta. Now, to determine this coefficient of kinetic friction for part D, we need to use the work done by friction, which is the force of friction multiplied by the distance it travels. So that's mu mg d cosine theta. Now, to put all of that together into our energy conservation equation, so we have our gain in potential minus, or plus our loss in kinetic, and our change in internal, and all of that equals 0. So this is one big equation for one unknown, mu, which is what we want to solve for. Now I need to make myself some space. So solving this for mu, what we end up with so I'd want to divide out all of this stuff here, move stuff to the other side of the equal sign, solve for mu. And I've got initial speed squared over 2gd cosine theta minus tangent of theta.